Let's talk a little bit about ionic compounds. These are very common. The Earth's crust has a lot of minerals, and those minerals are ionic compounds. Ionic compounds are present in the foods that we eat. Our body has a lot of ionic compounds in it. Ionic compounds are generally very stable because the ionic bonds are very strong, the attraction between opposite charges. And so typically ionic compounds are solids at room temperature because they hold together really well. So here are a couple of examples. These are ionic compounds that you might ingest. Morton light salt is a mixture of sodium chloride and potassium chloride. It's lower in sodium because some of the sodium has been replaced with potassium. It doesn't quite taste the same, but I guess it's better than nothing. And Tums contain calcium carbonate, which is also an ionic compound. And then here are two examples of minerals. Calcite is a different form of calcium carbonate. You probably wouldn't want to eat that because you might break your teeth trying to chew it, and it would literally sit like a rock in your stomach. And this is called trona. This is a crystalline form with this crazy formula. Thankfully, we don't need to learn how to name that one. I don't know why they gave you a picture of that one. So we're going to learn to write names and formulas, for ionic compounds. So when you're writing the formula, when we first start doing this, before we get really good at it, you're going to need to write some things down. There's some work to do. And I highly encourage you to go for it and actually write the stuff down. Because once you get it, then you won't need to do that anymore. We're going to start out by writing the symbols for the cation and the anion. So the symbol for the metal cation, include its charge. Then you write the symbol for the non-metal ion with its charge. There should be a word in there, the non-metal anion with its charge. We need to know what the charges are because that's what tells us how many of each, what the ratio is, because they combine in a way that they're electrically neutral. So we're going to adjust the subscripts so that we get an overall zero charge, and then we want to double check at the end that it's all going to add up to zero. So ionic compounds always have positive and negative ions. The first element is usually a metal, and here's that one exception that we need to know about, ammonium ion. The metal comes first. I think of metals as being masculine and the non-metals as being feminine, and so this follows the same pattern as like a formal invitation, formal wedding invitation. It's addressed to Mr. and Mrs. John Smith, right? Why do we do it that way? It's just a custom, right? You don't see some people going Mrs. and Mr. and other Mr. and Mrs. It's always Mr. and Mrs. just because. So the metal is the masculine. He's the Mr. He goes first, okay? Metal first, then the non-metal. The sum of the charges of the positive ions has to equal the sum of the charges of the negative ions. The total charges have to add up to zero, and then we're going to see that the formula for ionic compounds is always the smallest whole number ratio of ions. Okay, so let's write some formulas. So write the formula for the ionic compound that forms between potassium and sulfur. So we need the element symbols. Potassium is K, and sulfur is S. And then we get the charges from the position on the periodic table. So potassium has what charge? Positive 1. So we write that as just plus. Skip the 1, we don't need it. So that's positive 1 because it's in group 1A. What's the charge on a sulfur ion? 2 negative. Sulfur is a non-metal, it's going to be negative. Non-metals are negative. And if we start at the noble gases with argon and we count backwards, minus 1 to chlorine, minus 2 to sulfur. So that's the charge. Once we have that, then we're going to look at, well, how many of each of these do we need? What's the smallest ratio where we're going to have it be electrically neutral?
2 to 1.
2 to 1. We need 2 of these to balance the charge on that. So if I put 2 potassiums, now I've got a total of +2 charge. And over here from 1 sulfur, I've got -2. And those add up to 0, or they cancel each other out. So then I write the metal first, followed by a subscript indicating how many. And then the nonmetal, if needed, a subscript to say how many of those. So K2S is the formula for the ionic compound that forms between potassium and sulfur. Any questions? Let's do aluminum and nitrogen. Symbol for aluminum is Al. Al. And nitrogen is N. What's the charge on the nitrogen ion? Count back from the -3. So 3 minus. The charge comes after the number because we don't want it to look like an exponent. And then aluminum, what's the charge on the aluminum ion? 3 positive because it's in group 3A. It's a main group metal. So if we've got +3 and -3, you just push one of each of these together. That's the smallest unit that's going to be electrically neutral. So AlN. It is very important that your capital letters be capitals and your lowercase letters be lowercase. So the lowercase l, the number 1 and a capital I, which is which, right? You can't tell. Capital I, I'm going to put serifs on it. The number 1, I'm just going to leave as it is. And for an L, I like to make a script L so that it's clearly different. And I've... So if you say I2, I'll probably know what you mean. There are some situations, though, where it becomes confusing, and then we just need to do everything we can to be clear.
Okay.
I actually changed the font I use on these slides because it had them all the same. L's, 1's, and capital I's all look the same. Now the I has bars on it, and the 1 is, kind of fancy, and then the lowercase l is just a line. Okay? What I don't want to see is I don't want to see ALN. Okay? This is a capital L. You just wrote it small. And you are welcome to do that with the rest of your writing. Engineers do that a lot. That's fine, but not in the chemical formula. That is not okay. Another one you have to watch out for, the difference between cobalt and carbon monoxide. It's just the size of the circle. So try to be clear, okay? So that's writing formulas. What about the names for these guys? Some compounds have common names, like NaCl is known as table salt, right? That's a common name. But all compounds have systematic names. A bunch of people got together, International Union of Pure and Applied Chemistry, got together and decided, okay, the whole world, we're all going to use this same system. And sometimes on the side we sneak our common names in, but we also understand the universal system, and so we can use that as well. So those are the systematic names. To name a compound, you have to know what kind of a compound it is, because there are different patterns for naming. Just like in different cultures, there are different patterns for naming children, right? Some cultures, people only have a single name. Other places, they have 2 names or 3 names. My ancestors came from Sweden. That's probably not shocking to you. Back in the old days, if your dad's name was John, then your last name, if you're a guy, would be Johnson, because you're the son of John. And if I as a woman had a father named John, my last name would be John's daughter, because I'm John's daughter. And so the last names were different every generation. Makes looking up your family tree a little tricky, right? Because it just keeps changing. But that was the system they used. We have different systems for different types of compounds, and so we just have to understand, okay, what culture, what kind of compound is this, so that we can use the appropriate system. So here we have ionic compounds, right? Some examples. And we can identify these because almost always the first element's a metal. And the only exception we need to know about is NH4. So here we've got sodium, aluminum, calcium, magnesium. These are all ionic compounds. So we can take ionic compounds and break them into two categories. Some metals always form ions with the same charge. And we've learned about those, group 1A, group 2A, group 3A. Aluminum is always +3. So the name of that ion is just aluminum ion. Other elements, other metals, can form more than one kind of ion. So iron can be a +3 or a +2 ion. Sometimes it's one, sometimes it's the other. And so you can't have the same name for an ion that has two different charges. So these are the metals that form ions with the same charge. So in group 1A, come on, pointer. In group 1A, +1. In group 2A, +2. Group 3A, there's aluminum, +3. Now, gallium and indium aren't highlighted, but we're not going to run into them very often. And then you need to know about zinc and silver. Zinc is always +2. Silver is always +1. Scandium is always +3, but we almost never see scandium, so I don't make a big deal out of that one. Okay? So for these metals, the name of the ion is the same as the name of the element. So Al3+, that's the aluminum ion. Okay? All of the other metals can form more than one kind of ion. And these are not things that we can easily predict from the periodic table. So here's a chart from your textbook showing some of them. Here's chromium. Chromium can be +2 or +3. Iron can be +2 or +3. Cobalt +2 or +3. It's like, oh, well, there's a pattern here. No, copper +1 or +2. Tin +2 or +4. Okay, so they can form at least two different ions. So then we have to specify in their name which one are we talking about. It's like King Henry of England. Which King Henry, right? There were at least 8 of them, right? King Henry VII, King Henry VIII. How do you identify them? With a Roman numeral. We use Roman numerals to identify these. But here, this isn't recording who came first, who's the father, who's the son. The Roman numeral is telling us what the charge is. So Cr2+ is called chromium 2 ion. The 2 is written in Roman numerals. I think we use Roman numerals instead of Arabic numerals because if you wrote the Arabic number a little small and it sank down, it might look like a subscript or something. And so we're trying to be less confusing. So we use Roman numerals. So here we've got tin 2 and tin 4. So that's tin with a Roman numeral 2 and tin with a Roman numeral 4. So let's have a quick review of Roman numerals. 1, 2, 3, 4, 5, 6, 7. That's probably enough. So those are the Arabic, the regular numbers. And Roman numeral 1 is a capital I. And 2 is 2 capital I's. And 3 is 3 capital I's. And you can see how if you just kept up with this, it'd be really tedious, right? It's not even as good as tally marks. We'll skip 4. 5 is capital V. I don't know why. Ask the ancient Romans. They made this up. V is 5. It's kind of convenient that 5 has a V in its name. 4 is 1 before 5. So it's 1 before 5. 6 is 1 after 5. So there's the 5 with a 1 after it. And 7 is a 5 with 2 after it, because it's 2 after 5 when you're counting. So those are Roman numerals. They keep going on. They get really confusing after you get past X for 10. I can never remember the rest of them because I don't use them. But this is good enough. So here's lead. So if we see lead IV, lead 4, we know that that's PB with a 4+ charge. Okay? You will be having to put some of these names into Mastering Chemistry. Mastering Chemistry knows the difference between whether you clicked a lowercase l key, the number 1 key, or capital I, right? They're going to look exactly the same on the screen. But if you did it with lowercase l's, it looks right, but Mastering Chemistry is going to say, nope, it's wrong, try again. And you're going to go nuts, and you're going to text me, and I'll go a little nuts before I remember to ask you, what key did you press to get those lines? It matters, okay? This is an older system that was used using suffixes and the Latin names. You should know that that exists. I won't give it to you on an exam, but if it shows up somewhere, you're like, oh, that's that other way. Go to the book and look it up. I don't remember what those are either. So here are some tricks for these ions. The metals in group 1A and group 2A have ions with a charge that's equal to their group number. And that's really also the same for aluminum. This triangle here, these are also predictable. Aluminum, zinc, and silver are the ones that your book gave you. They didn't mention cadmium, indium, and gallium because they're really unusual. But here, aluminum, gallium, indium, there's 3 of them. Here, there are 3+. Down here in the triangle, we have 2 of them. They're +2, and here's silver at the point, and there's a +1. You can also think of going downstairs, 3, 2, 1. Okay? So, groups 1A, 2A, 3A, zinc and silver, no Roman numeral, because you don't need it. My oldest son, James Kawagoa, we don't call him James Kawagoa the first, right? This is extra unneeded stuff, right? You only start putting numbers if you need them. Now, if he had a son named James Kawagoa, they might call him James Kawagoa II or James Kawagoa Jr., but you don't use it unless you need it. We're not going to use it for these because we don't need it and we don't want to write extra stuff. So groups 1A, 2A, 3A, zinc and silver, no Roman numeral. I'll be saying that phrase over and over and over again. Any other metal ions, put a Roman numeral on it. Okay? Group 1A, 2A, 3A, zinc and silver, no Roman numeral. Okay, so that's cations. What about the anions? There's polyatomic anions and there's monoatomic anions. So mono is a prefix meaning 1, so these just have 1 atom. These are going to be nonmetals. We've learned how to predict the charges from the periodic table. Here are the 2 basic methods, the group number -1, or the one that most people seem to like, count backward from the noble gases, -1, -2, -3, because that doesn't seem like math, whereas subtracting does. Oh, you know what? That is wrong. How many years have I been using these slides? It's not group number -1, it's group number -8. Good grief. Okay, group number -8. So those are the charges. What about the names? So these are nonmetals. I think of them as being female, right? Traditionally, when a woman gets married, she changes the end of her name, right? Her last name. So these act like women, and they change the ending of their name when they become part of a compound, which is kind of like getting married, right? You're becoming part of this new thing. So fluorine, when it's an ion, it's fluoride. Chlorine, chloride. Bromine, bromide. They all change the ending to "ide." Now, notice this base name here. Oops. I often see students write flour. Fluoride. There's no flour in fluoride. Fluoride. It's gluten-free. Okay? There's no flour in there. It's UO. So if you write it out and you see the word flour, switch the vowels. Just makes me laugh every time I see it. Which, you know, having me laugh at your paper is not necessarily a bad thing, but it's not necessarily a good thing either. Okay, so putting these things together. Binary ionic compounds, 2 different elements, 1 metal, 1 nonmetal. The name takes this form. You name the first one, and then you name the second one. So you've got the name of the cation and a space, just like you would with your name, and the name of the anion. Remember, she changes the ending of her name. These are not proper nouns. We do not capitalize them. Okay? They're just like regular old nouns. So KCl, if we're trying to name that, there are 2 elements here. There's potassium and there's chlorine. Potassium is in group 1A. It does not need a Roman numeral. So the name of potassium ion is potassium. Chlorine is a nonmetal, forms a -1 ion, and so you change chlorine to chloride, and then you put those 2 names together. You've got potassium chloride. CaO is 2 different elements, calcium and oxygen. Calcium doesn't need a Roman numeral, so there's calcium, and oxygen changes the ending of her name to oxide. Calcium oxide. Any questions? Let's practice. So, name the compound Ag3N. Let's call him Aggie. No, we can't do that. We can't make stuff up. So we've got 2 elements, right? What's the name of the first element? Silver. Is that a metal?